based on a white paper titled Generator Hybrid Grounding, written by our presenter, David Shipp, and Sergio Panetta of I-Gard. The paper discusses typical grounding practices and ground fault protection methods for medium voltage generator stators, and it highlights their merits and drawbacks. The paper pays particular attention to applications of multiple generators connected to a single bus. We have made this white paper available to you today, and to download a PDF of the paper, simply click on the Download Generator Hybrid Grounding button located on the right-hand side of your console. So now let me introduce today's speaker, David Shipp. David is a registered professional engineer and principal engineer for Eaton Electrical Systems and Services Division. He is a recognized expert in power system analysis and has worked in a variety of industries. David has spent many years performing the engineering work associated with his present-day responsibilities, which include a wide range of services covering consulting, design, power quality, arc flash, and power system analysis topics. Over the last few years, David has pioneered the design and application of arc flash solutions, that is, modifying power systems to greatly reduce incident energy exposure. He has also written over 65 technical papers on power system analysis topics and has received the IEEE Industry Application Society Prize Paper Award for one of these papers. David has more than 12 technical papers published in IEEE IAS national magazines and one in EC&M magazine as well. He is very active in national IEEE organization and helps write the IEEE Color Book Series standards. David presently is the chair for IEEE I and CPS-sponsored working group on generator grounding, and he has spent 10 years as a professional instructor, teaching full-time and occasionally serves as a legal expert witness. And finally, David is an IEEE fellow engineer. Quite a resume. With that, let's turn the session over to David so that he can start his presentation. David, the floor is yours.
Good afternoon, ladies and gentlemen. Thank you so much for your time. I was very pleased when Sergio Panetta asked me to participate with this. Sergio and I both serve on this grounding committee that we mentioned, and what we're going to do, in addition to the white paper, we're going to summarize some of the background support material, that white material, and I'm going to present to you, as the chair of the IEEE working group, some of the things that we found and talked about. So the summary here will give you some of the information that's all related to the research that we've been working on in the last 10 to 12 years as this working group. The key point is what we found in terms of medium voltage generator and protection and grounding has probably the neatest and latest thing in the last 50 years. It's actually just gone into the latest ANSI standards for generator grounding and protection. So with that, that should give you a background. If you'll notice the working group, we mentioned their name. Sergio is the I-Gard participant, obviously, here, but there's a wide range of other people from GE and most manufacturers, in my case, for my company, consultants, relay manufacturers, and so on. So anybody that has anything to do with generators and the protection of it has had somebody involved with it. That's fairly good committee chair there, so I won't spend more time on it, but you know that what we're presenting is the working group findings. Okay, the problem to find, there's actually been 5 technical papers presented on this, and we're going to summarize the key highlights of these, and at the end we'll tell you where you can go get these additional papers in addition to the white paper as well. Parts 1 through 4 was the problem to find, grounding methods, protection methods, conclusions, and then the last one is switching transients, so that makes sure when I do the solutions I don't cause another problem to cause the value. We're going to talk about all of these to a certain amount. Let's look at part 1, the problem to find. What was happening? When this first started many years ago, and I'll actually show you in the next particular slide, the insurance industries came to us and said, we've had some failures in generators, and we expected it was protected just like it was supposed to per the standards. We expected to be able to repair it very quickly in the field, and when we tore into it, the damage was massive. It had to be sent back to the factory. We were out. It was out of service for 4 months, and it was a multi-million-dollar loss associated. After the second one, they really pushed us, and we finally decided to form a working group to actually study the problem. And what we're going to do is really show you what some of these are. in a lot of industrial concerns or peaking plants for utilities and so on, they'll have a lot of medium voltage, multiple low resistance grounded sources. The key point is with generators, you do not want solidly grounded, and ungrounded is another issue and problem we'll talk about later. The point is there's multiple ground fault sources, and if you look at the particular diagram on the right, you will see part 1, medium voltage and multiple low resistance grounded sources. And what we've done is just show a very typical cogeneration industrial concern where I've got a utility tie down to 13.8 kV, for example, 1 to 2 generators shown here. There may be more complex system. It may be a 4160, but it's an industrial commercial concern at medium voltage. Let's look at some of the damage that got us started. This is one of the generators that the insurance company brought to it. If you'll notice, the wedges are removed. You can see the damage in the middle of the stator that was done, and it was not melted everything. You can tell that it was very noticeable, and they started looking more into it. And if you look at it very close, you see where it burned, and the key point is burned into the iron. It's not just messed up one coil, it's actually burned into the iron. You see it by the wider colors in the iron itself. When they looked at the end runs, there was so much forces, the end run moved and caused wedge loosening, which says they had to redo a lot on the windings there as well. And when they got it apart to rewind it, you can see in the middle how the iron was burned. As soon as I burn the iron and short iron out, it becomes a hot spot. You have no choice but 100% rewind the stator and replace the iron. And this is the key reason it went back to the stator. And if you'll notice, just during the coast down phase with a fault, you see the middle of the rotor where all the heat damage put it out around. They had to really redo the rotor and or replace it as well. So the point was that they expecting to replace a couple of coils and redo it in the field with 400 amps available ground fault current. They did not expect it to be very much damage. Our committee looked at this and says there's no way we could have this much damage with only 400 amps. So we started looking at it in great detail. Let's look at it in conceptual standpoint real close, and we're going to reduce it to its simplest forms with just one generator and one transformer. That helped us get a handle and find out what was on. If you'll notice the ground symbol on the generator on the left, that is essentially the ground fault that we assumed has just occurred. And if you'll notice with two sources and both generator and transformer breaker closed, there theoretically will be a total of 800 amps of ground fault current available. And we wanted to look at both pieces and say what's going on and what impact does each one have to the generator failure or windings. What we did is we started to look very closely at the arc energy. In other words, what's heat's happening. And we'll focus for the most part on the graph on the right. At the very bottom left-hand corner is where the arc initiates and starts. Time starts there. The time going horizontally along the bottom from out to about 0.1 seconds. And if you notice, as the fault occurs, the system, meaning the generator, the transformer that's backfeeding through the main breaker, follows that arc and adds heat and energy to it. At 0.1 seconds, you'll notice the graph stops and goes horizontally. That's because at 0.1 seconds, that's the breaker clearing time of the generator, and once the generator breaker comes open and all the protection turns it off, I lose that ground fault current from the external source. The breaker is open, I can backfeed no more. Now if you look at that, it's about 800 watt seconds. It's going to cause some damage, it's going to be noticeable, but it's field repairable. Then we went and said, okay, that takes care of one part of it. Let's go do the same thing on the second one. But now we had to look at the generator. In the same graph on the right, you'll notice it forms a curve that keeps going until a certain point where it goes horizontal at the top, and I'm talking about the right-hand graph. The key thing you need to realize is that the scale on the vertical axis is dramatically different. Remember, it was about 600, 700 watt seconds. If you'll notice now, this one on the generator is 6,000 watt seconds. What happens is once the generator breaker opens, the controls say stop the turbine, stop the field, turn everything off, but it still coasts for seconds, and there's a dramatic amount of stored energy in the inductance in the rotor and in the generator, and it's going to contribute the 400 amps amount inside the zone of the generator until all the energy is dissipated or the turbine starts rotating. Now, if you'll notice, if you look at the graph at the bottom, it does not go horizontal, meaning there's no more energy left to burn iron until I'm in the 3 or 4 second range. This is a big eye-opener to all of us. We suddenly realized that most of the damage occurs after the breaker is open, after the protectionist says go offline, and that we really had a problem where there was absolutely nothing with the current practices that we could do about it other than accept massive damage. So we all started scratching our heads and said, what can we do about that? Well, he says, well, let's go compare ourselves to some of the industry that's already been, that's had problems that don't have a lot of these problems. So we went to the utility industry, and a lot of utility generators, like, for example, a 200-megawatt generator that goes from the generator to some bus to a step-up transformer, then feeds power out on the grid on the transmission line system. Since there's one generator, one transformer signal, they will just high-resistance ground the generator only, not the 400 amps that the power system needs at 13.8 in an industrial concern, but say 10 amps. We went through the same math, the same scenario, but said let the fault current last until the energy's gone, or until the as far as burning, but we're externally limited to only 10 amps. Not 400 amps, but 10 amps. And if you'll notice the curve on the right, does exactly the same way and procedure as the other one, except for it ends out around 20 watt seconds, not 6,000. And then suddenly realized on the energy difference how much the system grounding of that generator itself affects the damage. Okay, once we came to that realization, we said, okay, what are we going to do to solve it? There's a lot of different grounding procedures or systems or theories out in the marketplace. So we said, let's look at all of them and say, what would happen or how could we change it to protect the generator? And so that's really part two of the working group. We looked at low-resistance grounded systems. We looked at effectively grounded systems. And for those of you that aren't really into power, effectively grounded is almost solid grounded. It's going to be other than solid, but it's almost solid grounding, and it allows you to have lower rated insulation, lightning arresters, and so on. We looked at reactance grounded with an inductor. We looked at high resistance, and we looked at ungrounded, and then combinations to say what makes the most sense to a system to protect my machine. All right, let's look at the low resistance real quick. First thing you need to realize, you always want to ground the source, not the load. And I'm talking about the Y point of the generator in this case. You'll notice the one line shows you the Y point of the generator to a low resistance grounding system. The typical size you most frequently see in industry is, so say, 200 to 600 amps. You want the total system amps less than 1,000. If I start having more than 1,000 amps, then the in-feed from the utility for the 0.1 seconds does unacceptable damage as well. Some cases we've seen as low as 100 amps, but these are very typical. There's many systems that we've run into where they're anywhere from 1,000 to 8,000 amps available, and the higher the available ground fault current, obviously when I get that ground fault in the generator, there's nothing left. So, but it gives you an idea. The reason we low resistance ground the power system is so when I get a ground fault out in the circuit remote, I don't burn up thousands of feet of 15 kV cable and their shields. I don't launch bushings into orbit. I let enough current flow so I know where it's at and trip something off, but I minimize the damage. That's the concept. Let's look at the advantages. It allows for sensitive ground fault current. It's just low enough that I can still determine it. I minimize the damage. The disadvantages, if there's too much low resistance ground current, is the possibility of this generator stator iron burning that we showed you. There's high ground fault current available with multiple sources because each generator I add makes it go higher. And there's a large variation of available ground fault current complicates the ground fault protective relay when I've got multiple sources. Doesn't mean it can't be solved, but it's not real easy. You got to work at it. Okay, let's look at the single point ground where you only ground one source at a time. It's the simplest. It's the lowest available ground fault current. Your ungrounded system, when you're offline, it leaves other parallel sources ungrounded. It requires special operating procedures. It's low cost, but there are all kinds of system implications. We'll talk a little bit about these in a little bit. Multiple point grounded, meaning every source is grounded through a separate resistor. That's simplified operation from procedures, but you have to realize you've got widely available ground fault magnitudes, sometimes excessively high. I've seen cases where there's been 11 sources in a power system, and when they operate a minimum of 2, I didn't have enough ground fault current for my ground fault relaying to work, but when I had all 9 sources in, there was too much ground fault current. And so you got to work through some of these scenarios in terms of what you're doing. The resistor sizing selection is more difficult because I got to look at minimum and maximum conditions. But it is the most common for industrial systems, for example, paper mills, cogen operations. I've had some utility peaking plants with multiple generators on one bus that would fit into the same category. It's the easiest to operate, but it's the most complicated from a protection standpoint. Let's look at some of them go back to the 50s, common ground with neutral switching. In other words, they'll tie all the Y points and sources together and only have one resistor. Saves a lot of money on resistors. What are the advantages? Low available fault current, simple relaying, add sources without changing available ground fault current. The disadvantages are safety, the neutral switching, lesser breakers, etc. In terms of they can be like a fault device, and you have a load break switch, it could blow up on you. You're going to get circulating third harmonic currents between all the generators. Severe cases, you'll have to derate the generators 30 to 40%. Special recommendations. After we looked at all the if, and, buts, you notice it says not recommended at the bottom. That was the working group's consensus. Let's look at the high resistance. You have very low transient over voltages. You generally limit the ground fault current to 10 amps or less. That's like the utility. It's minimal damage, but with only 10 amps flowing through a large power system, you have no idea where the ground fault is. And if I have to go into continuous operation, have a ground fault sound alarm and keep on operating, I can't do that much above 4160, and it must be a very small system. And as a one system or a generator only, there's a lot of ifs, ands, and buts with this. We would love to be high resistance like the utility, but when I put it in a complicated power system, the system becomes too large to live with high resistance only. Let's look at a unit connected. What a unit means, one generator, one step-up transformer, all the power is at, say, 115,000 volt out to the grid. Well, there's only one generator. I can high resistance ground, as we've shown here, and it's typically less than 10 amps. This is very typical of a utility generation site. With that in mind, now let's just talk and do a quick review of grounded and ungrounded systems. If I go ungrounded, the concept back in the early turn of the century to the 30s and 40s and even today is I can get my first ground fault and no current flows and I can keep on operating. Well, that's not true. When I say that, it's not that you don't have any current flow, but it's very low current. If I put a solid ground fault on this ungrounded system, and this was, in this case, is real numbers from a 13.8 kV generator with its generator breaker open, and you get a solid ground fault on one phase, we get about 5 amps flow through the ground path, and it returns through the distributed capacitance of the insulation system between the other two phases. And you have the amps, so it's not that there's 0 amps flow, but there's very low amps flow. Okay, it's also subject to high transient over voltages. But if the fault's solid, then the service continuity they think it is. And of course, you don't know where the fault is. There's not enough current flowing to determine where it's located. Let's look at the voltages that go with that current. Point A on the left is with no ground fault current, and if you have the dashed lines indicate the phase-to-phase voltages, the solid lines are the phase to ground, and the horizontal line represents the ground plane. If under no ground fault, even though I'm ungrounded, there is no voltage differences to speak. And let's say at 13.8 kV, I'll be 7960 volts to ground on phase A, 7950 volts on phase B, and 8000 on phase C. They're slightly off. They're close to 0, but not exact. If I get a solid ground fault with only 5 amps flow, then all the voltages with respect to ground shift up vertically as on the right-hand side. And essentially, I end up with a lot of I've got over voltage but no amps. Okay? Now, let's look at the solutions we looked at. There's 5 different ones we look at. We're going to say, well, let's leave the generator ungrounded and just low resistance ground the system. And look at the pluses and minuses. Then we looked at high resistance grounding of the generator and low resistance grounding of the system. We looked at hybrid grounding, which we'll show a little bit later. And then we looked at generator and source high resistance with bus grounding. And then all sources high resistance grounding. We looked at all the different options that made viable sense in the real world and looked at the pluses and minuses and what can we do for it. Let's go to the generator ungrounded and the system low resistance grounded, which is obviously the least expensive. In this case, the utility transformer's got a 400 amp resistor or low resistance ground, whatever the value is, a few hundred amps typically, and I've left the generator ungrounded. What that means is, if I get a ground fault down in the system, in the circuit, in the cable someplace, all the ground fault current's going to come out of the 400 amp resistor and the utility source and feed it. But the transient over voltages, all the things involved are covered. Everything's fine. Now, assume for a moment that the ground fault now is on the generator terminals, which is what we're looking at, and the fault has to backfeed through the two breakers into the generator. I still don't have transient over voltages. I'm getting 400 amps or 600 amps or whatever it is into the generator, and then the 50G function as the ground fault trips the generator breaker off. At the instant I trip the generator breaker off, what do I have? I have an energized source. I'm still running. I've got an arcing ground fault most likely and no ground fault source. So I'm ungrounded for the generator by itself. This approach takes care of the system, but it leaves the generator very vulnerable. Here's the thing that most people do not realize or understand. And what I want to walk you through this is that if I have an ungrounded system and I get an arcing ground fault, not a solid ground fault on this ungrounded system, but an arcing, it arcs, it goes out, it arcs, it goes out, what happens? At point A in time on the left, it shows you the line to neutral voltages of the three-phase system. At point B in time, moving to the right one spot, is the instant after the very first ground fault occurs, and you shift all the voltages up vertically. Now, bear in mind, the copper, for example, let's assume in the generator winding, I arc through the insulation from the copper winding to the iron core. An instant after the ground fault occurs, I shift up all the voltages. The voltage difference between the copper and the iron core is zero, and Ohm's law says with zero voltage across an impedance, which is the impedance of the arc path, you're going to have essentially no current flow. So the arc very typically goes off. I charge it up. I've left a trap charge, capacitive trap charge, on that phase with respect to neutral. And if you'll notice, there is a horizontal line with what we call an artificial neutral at line to neutral voltage above the ground plane. The arc has gone out, mind you, and left a trap charge. But in the meantime, the generator is still rotating at 60 cycles per second, so the voltage magnitude of the faulted phase is going to follow the dashed line that you see on the screen. 1/2 cycle later, the instantaneous voltage across the fault path was -1 and +1, or an absolute value of 200%. If it arced at 100%, what do you think it's going to do at 200%? It generally arcs again, and you see a little blip at just below the horizontal line indicating a spike of current. And what happens? All the stored energy and the inductance and capacitance of the phase now overshoots, and they go -200% very typically. And if the arc goes out again, I am now rotating at -3 per unit. And the process goes again, and in 3 or 4 arcs, you can see I can be at the top and where it says 5.5 per unit. Now, the line-to-line voltages around that delta are still line-to-line magnitude, but the voltage to ground is very high. How high can it go? The answer is infinity if I got enough time. Somewhere between 500 and 700%, I arc to ground and I form a three-phase fireball, and there's nothing left. And most people say, well, that doesn't happen to me. It doesn't happen very often. Well, we put this on the computer, which is the 5th paper. And if you'll notice, we simulated this on the Transients program, and on the graph you'll see the fault is initiated on the first dashed line to the left, and since it's ungrounded, and the breaker's closed, but the generator's ungrounded, the source isn't, though, you get little blips of voltage, just the arcing for a very short period of time. At the second vertical line is where the circuit breaker opens. This is a neutral breaker, leaving it on the ground, and you start seeing the voltage escalating, going up, and then all the red on the side is when I get high enough, I start getting the high-frequency natural frequency ring between the capacitance of the insulation and the inductance of the iron core of the generator, and it goes into high-frequency resonance. And if you'll notice these magnitudes, at the bottom one, it's like -50 kV, and I'm on a 13/8 system here. And it walks you through some of the stuff. In other words, we had to prove that this system mathematically actually worked. Nobody was going to let us put the fault on the system and measure it. They said, well, that's on line to neutral. I put the resters on it and take care of that. Well, I'll fine. Look at the neutral to ground voltage. It's doing the same thing. On figure 11, I'm at 45 kV on neutral to ground on my generator, and you'll flash over the neutral point, too. We've actually had some neutral ungrounded generators flash their neutrals over, and now we knew why. Okay, next slide. Here's a real-world scenario. This is a 13.8 kV. It's a tap box. And if you'll notice, on this ungrounded system, it wasn't a generator involved, but it has to do with 13H system, and I want to show one that's worked. Remember, phase A is the arcing voltage. The voltage to ground of the lowest magnitude is the phase that's arcing. The highest voltage are the other two phases because the other two phases have line-to-line voltage added to that line-to-ground voltage. So when it finally goes to a fireball, it goes phase to phase, and if you'll see a perfect case of this on A and C phase, arced into a fireball on a three-phase. Now, obviously, then it became a big three-phase fireball inside, and there was nothing left. It took a $1 million transformer with it. All right, let's look at a generator. This is an 11 kV generator with one of the neutral switches, and they had 4 generators, and they only had one of them grounded. The other 3 were ungrounded, like we talked about earlier. They developed a ground fault in the generator, and the voltage escalated, and it went phase to phase. When it finally went phase to phase, the other 2 phases, the energy is now 10 times, 100 times higher, something like that, if you look at the damage. Compare that to the damage of the first generator that had 400 amps. The damage was even worse on the ungrounded than it was on the grounded. Okay, looking back, it burned up not just a couple inches of iron, it burned up 14 inches of iron. It would have been cheaper to replace the generator, except it was a 1955 generator, and you couldn't get any of them built to fit the turbine and everything, so they had no choice but to spend the rebuild function time. Look how bad the iron is burned in this case. Dramatically worse than the resistance grounded one. Both were very costly. All right, let's now go to the next slide with part 2. It says, well, okay, if I want to prevent that, how do I prevent that from happening? This is almost ungrounded on the generator. It's high resistance only. The power system has a 200 amp grounding resistor on the left. And essentially, for any ground faults out in the system, the 200 amps is going to take care of the requirements of the system. If I do get that ground fault on the generator, I'm going to backfeed 200 amps. Their protection will trip it off. But if you notice now, I've got a high resistance grounding scheme that limits, in this case, to 8 amps. And what does that mean? Well, once the generator breaker clears, I am not ungrounded anymore. And if I'm not ungrounded, then those transient overvoltages that I showed you previously do not build up. I just lock it at a line-to-line voltage on my unfaulted phases, and I can live with that. I can't live with 500, 700%. Well, now we looked at it. The previous case with high resistance on the generator only had one very big limitation. I could never run the power system with the generator only. And in many cases in industrials, that's not acceptable to them. They want to be able to run on any source that happens to be available to them. So then we came up, I've got to be low resistance, but I want the generator to be high resistance, and that's how the working group we came up with the idea of a hybrid. Hybrid is essentially low resistance and high resistance grounded together. For example, you're showing a contactor here on the right, and it's normally closed, and there's my 200 amp low resistance grounded resistor, and I got, say, 10 amps out of the high resistance scheme in parallel with it. So anytime I get an external ground fault, I'll get 200 amps out of the LRG and 10 amps out of the HRG. The sum is 210 amps out in the system. Is it 200? Is it 210? That's not enough difference to get concerned. I still make my protection work. But what the hybrid says is once I get a fault in the generator, the protection says ground fault or protection. When I trip the main breaker, I simultaneously trip the 200 amps off and just leave it high resistance only to take care of the generator during the coast down phase. Okay, so what we did is we walked through that and we went through the transients issue. Now, if you saw this similar graph before ungrounded, when I tripped it open, the voltage escalated. If you'll notice, there's no escalation anymore once it comes open because that 10 amp grounding resistor, high resistance, takes care of it. You do see it go into high frequency, which was a surprise to us, but we're only about peaks of 20 kV, not 60 and 70 kV. It's the high frequency is there, which was a surprise to us, but the magnitudes and the escalation is not there, which is infinitely better. We also said on the neutral voltage that had a similar one, we put a snubber circuit in, which is an RC device that sucks up the high frequency. And if you'll notice, once we did that, the neutral to ground voltage went from the equivalent high frequency from before to just little spikes of 10 kV or so with an arrestor. It says all it takes care of, and it becomes a non-issue. We then put a snubber on the surge protection on the front end of the generator, and all that high frequency stuff, almost all of it went away as well. And although it's not in the papers, it was a very simple solution, and we found out, wow, we found a way to make it all happen. Okay? We looked at some of the other solutions, and here, if you'll notice on the example, we have a grounding transformer in the lower right, and it's just shown as it could be a zigzag, it could be a Y delta transformer, but I've created a Y point to go to a 200 amp grounding resistor, and we call this bus grounding, and then all the other sources are high resistance to take care of it. Now, this works, and it's a good choice. I have to buy an extra breaker, I have to buy a transformer, I've got to buy a lot of cable, it can be more expensive. Then I have to do high resistance on the transformer and other areas. It's not a bad scheme, it can work, but a lot of the times it's more costly. There are some systems where I've seen them do this. One other area was that when I get a low resistance ground fault, I just trip all my sources and do that. That would be the same as having a 200 amp resistor on a transformer and tripping the transformer offline, because when you do that, you lose all the power to the system that would occur. It's a different tripping scheme using that same concept. All of these are legitimate. They just can be more involved. Now, with that, we've tried to cover all the issues we've done. A lot of these things we've talked about here are covered in the white paper that's available to you. There are the 5 different parts and papers we mentioned. In the hybrid grounding paper is a reference to the IEEE reference if you want to go get those available to read more on what we've talked about. It will tell you how to go do that. And with that, I thank you for your time in my formal presentation. I want to turn it back over to John Dedad for the question and answer period.
Okay, David, thank you very much. Excellent presentation and very informative. A few of you have already submitted some questions, so we're going to jump right in. But while our presenter is answering your questions, please take a moment to answer the feedback form that will appear on your screen very shortly, if not already. If you have pop-up blocker technology, again, we ask you to disable that so you can receive the form. All right? Let's start with the first question. Can I use a zigzag transformer on the generator bus to limit my fault current to a minimal value regardless of the number of generators online?
The answer is yes. Go back to those last slides. Remember I showed you a transformer on a breaker that goes to a resistor? The zigzag transformer is a grounding transformer or one-way type of a grounding transformer. However, you can't just take the zigzag and solidly ground it. If you do, you become reactance grounded, and it's another way of creating huge voltage transients under ground fault conditions. You can use the zigzag off the bus to feed and make sure you connect the low resistance ground resistor to it. Then you can just high resistance ground all your generators. That's definitely a workable solution. It tends to be more expensive in most cases, but it is a very viable solution. You could also use 3 single-phase transformers connected to Y delta and be the equivalent of the zigzag, but then it takes up more space. These are all viable solutions.
Okay, next question. What size generators would benefit from the hybrid approach?
What's it worth to you? I hate to say it. I have seen them applied at 5 megawatts all the way up to 100 megawatts. They're definitely continuous run. The key thing is medium voltage. All right. The reason I say that, I would put these on smaller generators depending how important it is to me. For example, I've done some work in the oil fields in Africa. If you fail the generator, it's 6 months sending it out of the country before I can get it repaired and then back into the country to work. That means I've got my whole system shut down for 6 months. What is that worth to you? I would do it there. Other cases, this is a standby or something, then I would think twice and say, does it make sense? But the key thing is we would want you to go through the thought process to determine what it is. The key point is that it's applicable to medium voltage. It's not a low voltage application.
All right. Next question. What are the dangers of running an emergency generator set, either 6.6 kV turbine or a 480 volt reciprocating engine? What's the dangers of running those gen sets unloaded?
Unloaded, opposed to grounded, just unloaded?
That's the question asked, yes.
Okay, well, on the reciprocating one, unloaded, the bigger danger is going to be to the engine itself, because if it's not loaded, you don't get good heat dissipation out of the reciprocating engine itself, the prime mover, not necessarily the generator, but the prime mover. And I know this, in the oil fields where they've run reship engines like this for lightly loaded, once a year they're rebuilding the engine itself. If they have it 50% loaded or more, it lasts for several years. I'm just going, that's not my expertise, but I'm quoting some of my customer response and some from the returbine ones. Now on the turbine one itself, if I got a turbine generator, there's a prime mover concern as well. It has to do with exhaust temperature, but that's a function of a load more so. You got to have enough airflow to keep things within thermal ratings. And again, on the prime mover piece, you need to ask the turbine and the recip manufacturers that. The generator has no problem sitting there just idling, doing nothing thermally, unless I get a ground fault or something, and then all those issues kick in whether or not I'm loaded. Because bear in mind, under the ground fault conditions, I'm not worrying about external load, but the fact that I'm turning and I've got stored energy in the field of the machine.
Okay, next question. I work in the wind industry. I see the generators considered are synchronous. Do you have a similar paper or reference specifically for wind farms?
No, but I have been asked that question a lot, and it's one of the topics that our working group is considering to address. The wind farms, I will never leave if it's a synchronous machine opposed to an induction machine, I want to ground it. I would high resistance ground every generator I had in my power system at the minimum, as long as it's a synchronous one. And then I would do bus grounding. So, for example, in a wind farm where you have a lot of different ones, I would bus ground because there's too many sources and just take care of the individual. Now, if they're induction machines, opposed to synchronous machines, they are not a source, and I don't worry about grounding the generator itself, but I must ground the bus and the rest of the power system.
All right. Next question. Is anyone using the hybrid grounding system now? If so, for how long?
Well, one of the committees, we know of about 80 of them installed over the last 4 to 5 years. That's what the working group knows. There may be more, but these are the ones that we know of.
Is there a cost comparison of the hybrid system compared to other systems?
I got to stop and think. It will always be more expensive because there's more hardware. Let me put it a different way. We looked at the economic piece of it, and obviously when I add more hardware, it's going to be more. What we looked at it was what it does to, in terms of repair costs once I have the problem. If I go the standard low resistance grounding systems and we looked at the economics and what it cost this particular, the failed ones up front, it was about a $3 million repair, stator, loss of power, and so on. The hybrid grounding, if you put it in correctly, we did this with a paper mill that had 2,200 amps of ground fault current available, went through all the math, and the energy to burn the iron in the generator with a hybrid was 5% of what it was if I just left it like it was before. And doing the math, if they saved the one ground fault incident in the life of the machine, they paid for the equipment 40 times. So it's looking at it a different way. Until I get a ground fault, it doesn't do you any good. Once you have the ground fault, it's like insurance on your car. Insurance on your car does you absolutely no good till you have a problem or an accident, then it's got to kick in and take care of things.
Okay, next question. I am still not sure what the purpose of hybrid is. Why not just use the high resistance grounding? Why should we add low resistance grounding under normal circumstances?
Okay, it goes back to power systems at medium voltages. When I get a ground fault on any power system where I would go high resistance only, let me say this: if I can high resistance ground only, that's always my first choice. Okay, when I go at 13.8 or 4160. The systems are getting fairly big. There's a lot of capacity of charging current associated with all the cable insulations and bushings and so on in the system. And when I get a ground fault, okay, the voltage will escalate per that graph very quickly. And when I add resistance, it dampens it out and dissipates the stored energy and never lets it build up. To do that, the grounding resistor current must be equal to or larger than the capacity of charging current. Some of these power systems will have 20 to 30 or 40 amps of capacity of charging current. When I go over about 10 amps, there's so much current flowing, I'm doing damage anyway, and I've lost my benefit. But if I don't let 40 amps or so flow, then I don't control my transient overvoltages, and I still blow up the insulation. Essentially, in summary, the power system external to the generator itself needs low resistance grounding to make all your protection work. You get to use 133% rated cable insulation instead of 167%. Translate $2 or $3 million in cable when you put it in if you only went. So there's some huge economic benefits to be somewhere in the middle. However, from the generator itself, if my power system externally could operate with the other ground fault sources, I would prefer to go high resistance only. The only key thing is, if I put that generator on a system and I'm high resistance only, if I ever lose my other sources and you want to run as the only source, it can't do that. Let me cite an example of that, and then I'll turn it back to you, John. We've had one case where there was like a 15 MVA transformer and system, and they had a 1 megawatt peaking generator that they ran a lot of the time for waste gas or something like that. They didn't have a prayer of running anywhere near the load with a 1 megawatt generator, so they just high resistance grounded the generator and let the transformer take care of everything else. And that was a very good compromise. But if you have like a much larger generator and you want to run part of the load when the utility transformer's out, I could not do it high resistance only. There's some system design considerations you need to think and say which makes the most sense for my system.
Next question. What is the best method to measure the charging current of the generator system in order to determine the high resistance ground current limiting value?
Well, at 480 volts, I'll go put a small ground fault in the system and measure it, but we weren't talking about that. At medium voltage, I much prefer to calculate it all the time because there's a huge safety factor associated with the person taking the measurements. The way we would do it is, and bear in mind the high resistance at 13.8 is to take care of the generator breaker and the generator by itself, because the 200 amps or whatever takes care of the rest of the system. What we do is I open the generator breaker, I lift when the generator is off, I lift the ground source, and I measure the capacitance from neutral to ground, and that's with a DC device, and it gives you all the capacitance of the whole system, the generator, cables, everything. Divide by 3, and that's my single-phase capacitance, and I can do the math and come up with what's needed.
Okay. You mentioned medium voltage escalating quickly at medium voltage. Mentioned voltage escalating quickly at medium voltages and large systems. You said 4160 or 13.8 kV. What about systems of 2.4 kV with, say, 16 2 to 4 megawatt generators in parallel and no utility? Would you still recommend low resistance on the high resistance grounding, the hybrid concept?
At 2.4 kV, you're standalone. My question is, how big is the power system and the cable? At 2.4, I can have a lot bigger system than 4160. I have taken 2.4 kV systems and high resistance only, but again, I got to meet that 10 amp high maximum charging current or less before I can do it. Most of the cables used at 2400 volts were actually 4160 volt cables just applied, so I don't have to worry about my cable being a problem. I go look at my available charging current for the whole total power system, and then I would make a determination whether I could be high resistance only or did I need low resistance. If I need low resistance, I'm going to go the hybrid for the generator and let it be low resistance for the system. If it's small enough that I could live with high resistance only, then I would seriously consider high resistance only for the 2400 volt systems. But it doesn't take a huge system or to finally exceed that 10 amp criterion. And this is based on IEEE research that's been done and practices for the last 30 to 40 years. So the 10 amps is a rule of thumb. It's not cast in concrete, but by the time you're in the 12, 15 amp, there's too much damage done by the amps over a period of time. So that's a rule of thumb that has 50 years, a good track record history with it. So again, it's a design criterion. You have to answer some questions, then you can decide.
Okay, what is the disadvantage of using low resistance neutral groundings, the 400 amp type, for each of three 2500 kW 4160 generators operating in parallel?
For external system, I've got 1,200 amps available, and I get a fault out on the system. The ground fault current will try to return back through the shields of your cables, and you will burn up your shields and be replacing lots of cable in a few years, and it's very expensive from the cable standpoint. You could go down to 300 amps. Our rule of thumb in the research of the years said about 1,000 amps is maximum. Now, that's the external system problem. Now, if I get any time in the life of the machine, if I get a ground fault on one of the generators, the other two generators are going to backfeed through the generator breaker for 0.1 seconds, for example, from each source. So I'm going to have, say, if you're 400 amps, you're going to have 800 amps backfeeding through the one generator breaker for 0.1 seconds. And that will be probably 3/4 as much damage as the 2 to 3 seconds inside the zone. We've done the math with some of the other applications, and when I'm over about 100 amps, it makes sense to go ahead and do it. Again, I'm protecting the generator itself and the service continuity, not the external power system. So that gave you both sides of the considerations.
Okay, for the hybrid method, what equipment do you use to open the low resistance grounding resistor?
In that last paper that we wrote and referred to, the fifth one, we actually go through the specifications for that. I need to give you the generic one rather than what Eaton uses. But I'll give you, it must be a device that operates in the same speed or faster than the generator breaker, meaning 3 to 5 cycles or less, and it must be able to interrupt the ground fault current. And the ground fault current would be the 200 amps or 400 amps. So it doesn't have to be a 20,000 amp power breaker, although you can use that. Okay? But we actually go through a lot of the specifications and the requirements that if you are going to do it, what you need to have. So it can be a breaker or a high-speed vacuum switch as long as it meets the voltage, the interrupting capacity, and the time issues. There's a control power issue, too, that's got to be compatible with your control power on the generator and your switch gear, but those are something you can work around.
Okay, next question. Is this an issue on smaller 12.4 kV generator sets that are solidly grounded? We have several hospitals that have 3 12-470-volt generator sets in a range of 1.5 to 2 megawatts that can be paralleled with the utility.
Yeah, that question's come up. If you have a ground fault in any one of those generators when they're running, you throw the stator away because you're going to put 20,000 amps into it, and there's nothing you can do. Solid grounding generators can be a real serious problem. The reason you get away with it at 480 volts because most of the time you don't have solid faults. You have much reduced fault current magnitude. The only issue is you have to decide, in this case, since it's emergency and it typically runs a half hour a month in a hospital, for example, do I want to go to the extra protection issue? And I've seen arguments both ways, and so you need to decide what it is. If you do get a ground fault in the generator when they're solidly grounded, it doesn't happen very often, but there'll be massive damage in the individual generator that had the fault.
All right, we have time for just 2 more questions here, I believe. If I'm understanding this question right, is it? I believe the attendee is asking, can an existing grounding system be upgraded to the hybrid grounding system?
95% of the ones that I know of have been installed have done that. They've retrofitted. So a lot of paper mills have done that. They're not going to change out their whole power system. So about 80% of the ones that we know of as a committee that have been installed have been retrofitted.
Okay. All right, this last question here. Do these issues apply to reactive grounded generators?
Reactants? The answer is yes. However, with reactance grounding, they're approaching solid grounding, and although the hybrid will help immensely, that 0.1 seconds till it gets cleared will cause some very significant damage, more so than most industrials are useful. The reason for reactance grounding, though, is typically if I wanted to be solidly grounded, but the external ground fault current was more than the generator could withstand, so they put just enough of an inductance or reactance in the neutral point to limit the external ground fault current to the 3-phase current. And it has to do with mechanical bracing of the generator for external ground faults. However, if I get a ground fault in the zone, I could put this in, and it'll help dramatically, but it's still going to have more damage than the resistance version. But it's going to improve it dramatically. I know of a couple instances where we were looking at applying it at 12.47 kV on a municipal emergency generator systems where the municipal systems distributed around town at 12.47, and they had to have solid or almost solid grounding to be able to run the distribution system, so it was a compromise. But the answer is yes, it will help dramatically, but I wish it could be low resistance instead of the reactance.
All right. Well, that brings us to a close of the Q&A session and to the webinar itself. And David, I want to extend my thanks to you for the excellent presentation and very informative answers. And to you, the attendees of this webinar, I extend our thank you for your time and attendance this afternoon and for the great questions as well. We hope to find today's events informative and of value to you in your job, and we hope to see you attending future webinars. Have a great remainder of the day. Thank you.
Ms. Shia?
Yes.
This is Raymond, the conference operator. I see that the streaming line has been. Actually, one moment, please. I do show that the streaming line has been joined. I'm not showing it in the conference. One moment, and I'll be more than happy to verify that information that for you. One moment.
Okay.
Okay. Thank you. Mr. Shia?
Yes.
This is Raymond, the conference operator. The streaming line has been reconnected. You may begin the conference.
Okay, great. John, would you like to go ahead with the next question?
Yes, I will.
Thank you.
All right, thank you. We seem to be back online here with the streaming audio. I do apologize for those technical problems here, but we're going to continue with the next question. You mentioned medium voltage escalating quickly at medium voltage. Mentioned voltage escalating quickly at medium voltages and large systems. You said 4160 or 13.8 kV. What about systems of 2.4 kV with, say, 16 2 to 4 megawatt generators in parallel and no utility? Would you still recommend low resistance on the high resistance grounding, the hybrid concept?
At 2.4 kV, you're standalone. My question is, how big is the power system and the cable? At 2.4, I can have a lot bigger system than 4160. I have taken 2.4 kV systems and high resistance only, but again, I got to meet that 10 amp high maximum charging current or less before I can do it. Most of the cables used at 2400 volts were actually 4160 volt cables just applied, so I don't have to worry about my cable being a problem. I go look at my available charging current for the whole total power system, and then I would make a determination whether I could be high resistance only or did I need low resistance. If I need low resistance, I'm going to go the hybrid for the generator and let it be low resistance for the system. If it's small enough that I could live with high resistance only, then I would seriously consider high resistance only for the 2400 volt systems. But it doesn't take a huge system or to finally exceed that 10 amp criterion. And this is based on IEEE research that's been done and practices for the last 30 to 40 years. So the 10 amps is a rule of thumb. It's not cast in concrete, but by the time you're in the 12, 15 amp, there's too much damage done by the amps over a period of time. So that's a rule of thumb that has 50 years, a good track record history with it. So again, it's a design criterion. You have to answer some questions, then you can decide.
Okay, what is the disadvantage of using low resistance neutral groundings, the 400 amp type, for each of three 2500 kW 4160 generators operating in parallel?
For external system, I've got 1200 amps available, and I get a fault out on the system. The ground fault current will try to return back through the shields of your cables, and you will burn up your shields and be replacing lots of cable in a few years, and it's very expensive from the cable standpoint. You could go down to 300 amps. Our rule of thumb in the research of the years said about 1,000 amps is maximum. Now, that's the external system problem. Now, if I get any time in the life of the machine, if I get a ground fault on one of the generators, the other two generators are going to backfeed through the generator breaker for 0.1 seconds, for example, from each source. So I'm going to have, say, if you're 400 amps, you're going to have 800 amps backfeeding through the one generator breaker for 0.1 seconds. And that will be probably 3/4 as much damage as the 2 to 3 seconds inside the zone. We've done the math with some of the other applications, and when I'm over about 100 amps, it makes sense to go ahead and do it. Again, I'm protecting the generator itself and the service continuity, not the external power system. So that gives you both sides of the considerations.
Okay, for the hybrid method, what equipment do you use to open the low-resistance grounding resistor?
In that last paper that we wrote and referred to, the fifth one, we actually go through the specifications for that. I need to give you the generic one rather than what Eaton uses. But I'll give you, it must be a device that operates in the same speed or faster than the generator breaker, meaning 3 to 5 cycles or less, and it must be able to interrupt the ground fault current. And the ground fault current would be the 200 amps or 400 amps. So it doesn't have to be a 20,000 amp power breaker, although you can use that. Okay? But we actually go through a lot of the specifications and the requirements that if you are going to do it, what you need to have. So it can be a breaker or a high-speed vacuum switch as long as it meets the voltage, the interrupting capacity, and the time issues. There's a control power issue too that's got to be compatible with your control power on the generator and your switch gear, but those are something you can work around.
Okay, next question. Is this an issue on smaller 12.4 kV generator sets that are solidly grounded? We have several hospitals that have 3 12-470 volt generator sets in a range of 1.5 to 2 megawatts that can be paralleled with the utility.
Yeah, that question's come up. If you have a ground fault in any one of those generators when they're running, you throw the stator away because you're going to put 20,000 amps into it, and there's nothing you can do. Solid grounding generators can be a real serious problem. The reason you get away with it at 480 volts because most of the time you don't have solid faults. You have much reduced fault current magnitude. The only issue is you have to decide, in this case, since it's emergency and it typically runs a half hour a month in a hospital, for example, do I want to go to the extra protection issue? And I've seen arguments both ways, and so you need to decide what it is. If you do get a ground fault in the generator when they're solidly grounded, it doesn't happen very often, but there will be massive damage in the individual generator that had the fault.
All right, we have time for just 2 more questions here, I believe. If I'm reading this, understanding this question right, is it? I believe the attendee is asking, can an existing grounding system be upgraded to the hybrid grounding system?
95% of the ones that I know of have been installed have done that. They've retrofitted. So a lot of paper mills have done that. They're not going to change out their whole power system. So about 80% of the ones that we know of as a committee that have been installed have been retrofitted.
Okay. All right, this last question here. Do these issues apply to reactive grounded generators?
Reactants? The answer is yes. However, with reactance grounding, they're approaching solid grounding, and although the hybrid will help immensely, that 0.1 seconds till it gets cleared will cause some very significant damage, more so than most industrials are useful. The reason for reactance grounding, though, is typically if I wanted to be solidly grounded, but the external ground fault current was more than the generator could withstand, so they put just enough of an inductance or reactance in the neutral point to limit the external ground fault current to the 3-phase current. And it has to do with mechanical bracing of the generator for external ground faults. However, if I get a ground fault in the zone, I could put this in, and it'll help dramatically, but it's still going to have more damage than the resistance version. But it's going to improve it dramatically. I know of a couple instances where we were looking at applying it at 12.47 kV on a municipal emergency generator systems where the municipal systems distributed around town at 12.47, and they had to have solid or almost solid grounding to be able to run the distribution system, so it was a compromise. But the answer is yes, it will help dramatically, but I wish it could be low resistance instead of the reactance.
All right, well, that brings us to a close of the Q&A session and to the webinar itself. David, I want to extend my thanks to you for the excellent presentation and very informative answers. And to you, the attendees of this webinar, I extend a thank you for your time and attendance this afternoon and for the great questions as well. We hope to find today's events informative and of value to you in your job, and we hope to see you attending future webinars. Have a great remainder of the day. Thank you.